response. So once we are done with this n equal to 5 part, all the above design steps we are going to repeat for the length n equal to 11. Since we have to note down and understand what is the effect of increasing the length of the filter. As in, we are expecting the performance of the filter should improve in terms of the pass band, stop band and transition band. So does it really happen? So that you have to observe by generating the filter coefficients for n equal to 11 and then plotting the corresponding frequency responses. So again, based on the same lines, initially uh, the specifications corresponding to cutoff frequency and the sampling frequency will remain the same, that is Fc and Fs. Herewith we are changing the length of the filter and we are passing it on into variable capital N1. So this value we will be entering from command window as 11. So followed by that, M1 will store the center of symmetry or the midpoint value according to N111. So herewith it will be 11 minus 1, that is 10 upon 2. So M1, the center of symmetry, will be at 5. So with respect to the center of symmetry 5, to the left hand side of the center of symmetry, there are in all 0 to 4 number of coefficients, and after 5 starting from 6 up to 10 they are the remaining filter coefficient values, the locations. So after the midpoint calculation we are computing the digital cutoff frequency again in the same manner as we did earlier. Followed by that we are computing HD0 separately with the formula omega C1 upon pi. That's the formula for the low pass filter at n equal to 0. Thereafter, once again in the variable n1, we are breaking up the entire n range into 50% of the values. That is the left hand side of HD0 as told before, since M1 is 5 coming up as a 5. So this will be 5 minus 1, that is 4. So as told before, N1 will contain the range from 0 to 4. So now this set of the range of values will be made use to compute HD1 set of filter coefficients. So again, this formula to compute the filter coefficient is followed according to the theoretical formula to design a low pass filter, an ideal low pass filter in FIR filter design theory. And again, n minus m at numerator and denominator ensures that we are designing the causal filter. So after that, again another set of, well, the range of n we are declaring the 50% of the coefficient values starting from m1 is now 5. So 5 plus 1 is 6, starting from 6 up to n1 minus 1, that is 11 minus 1, that is 10. So from 6 to 10, the range of values of n2, for this range, the filter coefficients will be computed into a variable HD21. And finally, in the HD1 variable, we are concatenating sequentially the filter coefficient values computed separately, as HD11 will come first, followed by that HD01, in line to that HD21. So overall the length of HD1 will be meant for the 11 coefficients. So followed by that we are displaying the values computed and stored in variable HD1, which will be displayed in the command window. Followed by that we are describing the rectangular window function in W2 variable, multiplying this window coefficients with HD1 and generating the causal filter coefficients and then displaying it in the command window. And similarly, yeah, of course, we are computing, followed by that, we are generating the frequency response for these rectangular window based coefficients generated earlier. So this is going to plot both the magnitude and the phase response for n equal to 11. So again, these lines are repeated for the Hamming window. For the length 11, W3 will now contain the window coefficients for the Hamming window, which will be later multiplied with the HD1, 11 coefficients in all. And for this filter coefficients, which are generated by multiplication with Hamming window, they are displayed in the command window. And finally, the frequency response is plotted for this filter coefficients. So accordingly, we have also to place the titles for the respective plots. So at the end of this program, you have to follow this exercise. So now you have to run the program, overall program, to display the filter coefficients and corresponding frequency responses. Followed by that, theoretically calculate the filter coefficient values HDN and compare those values with the practical values generated by this program. Observe the frequency responses generated by rectangular and Hamming window for n equal to 5 and n equal to 11. Now in the same program, try to extend the program for the use of Blackman window. MATLAB contain the function Blackman. So the way Rectwin and Hamming we have called in the program, you have to call for the Blackman window function and compute the corresponding filter coefficients for n equal to 5 and n equal to 11, and also display the frequency response corresponding to Blackman window filter coefficients. And now compare this response generated by Blackman window with that of rectangular and Hamming window. As an additional exercise, you can try designing the high pass filter for the same design specifications and note down the filter coefficients values and the frequency responses. So this is to be done in the software only. Thank you.